Hi folks. Today we're looking at derivative functions. So we've already been able to find some tangent slopes, and we're going to look at what it means to have a function that gives the tangent slope anywhere. And to begin with, maybe we'll look at this idea. Find the steepness of this function at 3 points. And then there's a for fun question. Now, I'm not going to go through the solution to this in real time, but I do want to think through some different ways of doing it. So here's option 1 by using our definition that lim as h goes to 0 of f of a plus h minus f of a all over h is going to give us the slope at a certain point. And I do it at one x value, and then I do it at another x value, and then I do it at another x value. Okay, so I found 3 different slopes. That's a lot of work. And you might think, well, maybe there's a better way. And so here comes option 2. We could do the general case that we've done before. Find f of a plus h, get a little formula for slope anywhere, like this one right here after I do all my differentiation, and then just sub in different values. And I get the same numbers, and you can automatically see that that is less work than doing this. It does seem a little silly, though, that we substituted x for a, and then we substituted a for other values. So here comes option 3. It says, if we're just going to replace a with values anyway, why not just pick a generic point, x, f of x, instead of a, f of a, so that you'd have f of x is this, and f of x plus h. It's still like kind of painful, just like it was for f of a plus h. And then the slope of the tangent is going to be the lim as h goes to 0 of f of x plus h minus f of x all over h. And that is once again going to give us a little formula for the slope anywhere. And so far we're just calling that the slope of the tangent equals. And then we can sub in. Option 3 and option 2 are essentially the same amount of work. But in option 3, we don't insert a variable that doesn't really need to be there. The name for this little formula of the slope anywhere is called the derivative of f of x. And that's what we're going to look at today. Now here come the notes. 3.1, derivatives. The slope of the tangent to f of x at some point where x equals a is called the derivative of f at a. And it's often written like this. We say f prime of a, or f prime at a. It looks like an apostrophe. And that's one of the notations. Since we might be interested in the slope at multiple points, just like we were in the question that was given to us to start with, it's often convenient to find a function that gives the slope at any point. So instead of finding f prime exactly at the point a, we're going to find f prime anywhere, or the slope anywhere. This type of function is called a derivative function, often written f prime of x. And the derivative of f of x is given by this, which looks pretty familiar. It's just instead of a's, we have x's. If you were going to get a differential calculus tattoo, this would be the one. This is solid gold. Okay? I don't recommend that you do get a differential calculus tattoo. I'm just saying, this is an important formula. It's really the underpinnings of all of differential calculus. The process of finding the derivative is called differentiation. So, the thing itself is the derivative. The process of finding it is not deriving, it's differentiating. It's different in French. It's le dérivé for the derivative, and dériver, the verb, for differentiating. In English, it's more annoying. Moving forward, we'll tend to find the derivative function rather than the derivative at a point. So this will be sort of our go-to thing. Now, here's one thing I want to stress. When you see f prime, you should think slope, okay, or tangent slope. That's what f prime is telling you, or the derivative is telling you. It's telling you about slope. Here's a short list of some accepted notation for derivatives. All these things mean the exact same thing. So f prime and y prime, that's really quick. This is called the Lagrange notation. It's often referred to as the Lagrange notation. Quick. Newton had his own slightly different notation that was kind of similar to the Lagrange notation. And it's quick. It doesn't indicate the variable for differentiation. Here, these ones here look a lot like slope, right? Change in y over change in x. So it reads dy by dx or dy over dx. It identifies the independent variable. It looks like change in y over change in x. It can help you know the units for your slope, but it still just means the slope of the tangent. And if you had a function, maybe you'd have df by dx. And lastly, you might see it written as d by dx of f of x. What that means is that you're going to differentiate this. So when you see it as d by dx, it's a verb. And it reinforces the idea that differentiation is a process that's being applied to some function. Like we go through the whole lim as h goes to 0 of f of x plus h minus f of x all over h, at least for now. We may end up with some shortcuts later. Okay. And this notation here in the last two is the Leibniz notation. And it has endured for a long time. So Leibniz is one of the co-inventors / discoverers of calculus. He's probably the less famous one compared to Newton. But this notation that he developed has endured. And like I said, some other mathematicians had their own notation. Newton had his own notation. Euler had his own notation that's very similar to Leibniz notation. These are the common ones we'll see. They all just mean differentiate or find the slope. So let's practice finding slope. We're going to find the derivative function for each, then find the slope of the tangent at the indicated point. So I'm going to think of this as f of x. Okay. And here's the idea. The slope anywhere, or the derivative function, is lim as h goes to 0 of f of x plus h minus f of x all over h. So I already know f of x. That's great. Off to the side, I'm going to have to figure out f of x plus h. And we've kind of gone through this before where we put in a plus h. But all it's telling you is wherever you see x in here, you're going to put in x plus h. Okay, so let's do that. 2x plus h all squared minus x plus h. Whenever I substitute in, I do it in brackets. I'm going to carefully FOIL this out. X squared plus 2xh plus h squared minus x minus h, or 2x squared plus 4xh plus 2h squared minus x minus h. And that is going to go in for f of x plus h. And I'm just going to follow this little formula through. So the slope anywhere, or f prime of x, is going to be, we're going to need some space, okay? It's going to be f of x plus h, so I just found that over here. There are no like terms to collect, so I don't have any extra work there. Minus x minus h, and that's minus f of x, which I'll also put in brackets. So f of x we already knew over here. It's 2x squared minus x. Now, I think a lot of people will want to just go ahead and cross some stuff out, but I want to show the whole process here. So if I get rid of those brackets up top, I'm going to have 2x squared plus 4xh plus 2h squared minus x minus h minus 2x squared plus x. And at that point, there are some terms that add to 0. Those ones are gone, the 2x squareds, and so are the x's. And I'm just going to follow this through and see what the limit gives me. So I've got 4xh plus 2h squared minus h. This is very similar to how we do it if we had f of a plus h. We're just going to stay in that x variable. And some people may want to go quickly on the division. I think you are way safer to do the correct thing of factoring and then dividing out. So factor out an h up top, and then you can safely divide out that h. So you're sure you're not doing algebraic magic, you're doing algebraic properties at this point. F prime of x is going to be lim as h goes to 0 of 4x plus 2h minus 1. And we'll keep following it through. So now I can actually put in that 0. I get 4x plus 2 times 0 minus 1, or 4x minus 1. Okay. This means, what we've found here means the tangent slope anywhere, at any x value. So we found the derivative function. Yay, because it asked us to. We want now the slope exactly where x is 100. So we'll have f prime, not of x, but of 100. I just sub 100 in. And this last part of finding the slope is super easy. Okay, it's going to give me 400 minus 1, or 399. That's a very steep slope. Does that make sense? Let's think about the original function would have been a parabola that opens upward. Yeah, out at x equals 100, it's going to be really high and also really steep. So this seems like a reasonable answer. I'm going to check it on Desmos, though. There's f of x. And on Desmos, I can just type in f. I'm on the keyboard here. And in the bottom right, if I press Shift, I get the prime button. So I'm going to ask it for f prime of 100. And it's going to tell me the slope there is 399. And if I zoom out, I can imagine, yeah, at x equals 100, it's real steep. In this video, we'll do 2 more examples together, and then we'll have some practice time. But essentially, we're just going through the same process again. So I'm going to call this function g of x. And just to sort of generalize from that derivative definition, if I want g prime instead of f prime, just a different function, then it will be lim as h goes to 0 of g of x plus h minus g of x all over h. So I know g of x. I just got to go off to the side here, and I think it's worth doing to the side, and find g of x plus h. So that will be 1 over 2 times x plus h plus 1. I think it's worth expanding that out. So that is 1 over 2x plus 2h plus 1. Now let's sub it in. So g prime just means the slope on g anywhere. I'm going to have nested fractions here, or stacked fractions, so I'll need a little extra space. And I put in g of x plus h. That is just 1 over 2x plus 2h plus 1 minus g of x, which was 1 over 2x plus 1. Now, I have a preferred way to deal with nested fractions. I like to just multiply by the common denominator of the littles. And if I do it to the top of the big fraction, then I do it to the bottom of the big fraction as well. So what I'm doing here is maybe a little weird, but it is definitely okay, because I've done the same thing to the top and bottom. And let's just see what we get. I'm going to try and color code this so that it's clear what's happening. I'm going to have 1 times the 2x plus 2h plus 1s will divide out, so I'll just be left with 2x plus 1 minus 1, that's the numerator up here. Okay. That times the whole green thing, but the 2x plus 1s will divide out, so I'll have times 2x plus 2h plus 1. And on the bottom, I will have h by 2x plus 2h plus 1 times 2x plus 1. What's really pesky there is that blue h. Everything else is not really a problem. Let's go back to blue color here and just clean it up. So what will I end up with on top? I'll end up with 2x plus 1 minus 2x minus 2h minus 1. On the bottom, I'll have this whole big mess. So it's a lot of fiddly algebra, but we're just following it through. And you can see up top here, the 2x's are going to add to 0, the 1's are going to add to 0. Let's see what we're left with. Lim as h goes to 0. of negative 2h all over h by 2x plus 2h plus 1 by 2x plus 1. And here's where the magic happens. The h's divide out, and I'm left with g prime is equal to lim as h goes to 0 of negative 2 all over 2x plus 2h plus 1 times 2x plus 1. Now my problem is gone. Now I can actually sub in 0 for h, so I'll get rid of the limit and see what happens. I'll have negative 2 all over. Check out this bracket. This will be 2x plus 2 times 0 plus 1. Okay, so that's just 2x plus 1. And then the other bracket is 2x plus 1. Or the slope anywhere is 2x plus 1 all squared on the bottom and a negative 2 on the top. Okay. That's the slope anywhere. We want, in particular, the slope when x is negative 3. So when you read that g prime of negative 3, it's saying the tangent slope when x is negative 3. And we just sub it in. 2 times negative 3 plus 1 all squared. Or that would be negative 2 over negative 5 squared, or negative 2 over 25. So that means it's a not very steep negative slope. Let's just take a quick look on Desmos. We're not going to go through all the steps of getting it to calculate slope. We're just going to see if it looks like a reasonable answer. So think about where x is negative 3 back around here. That does look like a negative slope, and it's not very steep. We could get it to calculate the actual slope there, but our answer looks reasonable. One last one to think about. So I'm going to call this one f of x again. It's okay to reuse our letters. Most commonly, we're going to see f of x. So I want to find f prime, or the slope anywhere. So we're getting the hang of this. F of x plus h minus f of x all over h. That finds the slope anywhere on any function. And so we have to go off to the side and find f of x plus h. And maybe a good plan here would be to pause the video and try this yourself, and then come back and check it out. Okay, and we're back. Hopefully you actually did that. 3 by x plus h. And hopefully you found the punchline to this question. So we're going to sub in. F prime is lim as h goes to 0 of f of x plus h, which I'll do in red, 3x plus 3h minus 2, minus f of x, which is 3x minus 2. And let's see what happens. I'll get rid of those brackets, but maybe you're starting to feel comfortable to just say, oh, the 3x's are going to be gone, and the negative 2's are going to be gone. That's totally fine. I would not be inclined, though, to combine my division cancellation and my subtraction cancellation in one step. Better to be correct than to be quick. All right, 3x's are gone, negative 2's gone. All we're left with here is 3h over h, and the h's divide out. And this seems fishy, so f prime of x is going to be lim as h goes to 0 of 3. And as h goes to 0, 3 is just 3. So it's saying f prime is 3. I mean, I guess then f prime at 4. There's no x to sub into, so it's still going to be 3. Seems weird. Let's think about the original function, though. Of course the slope's 3 everywhere on this. This was a line with a slope of 3. And in a way, we just went through the worst possible process of showing that the slope of that line is 3. It's super cumbersome compared to, say, grade 10 just saying y equals mx plus b, slope is 3. But it's nice to know that our techniques are consistent. And that's an important property in mathematics. If we have techniques that give us different results, then we're feeling pretty nervous about those results. Okay? So if you notice that the slope is 3 everywhere, well, I guess you could answer this quickly. Most of the time we won't be asking about lines. Just thought it was fun to throw it in there. So I'll give you a few practice questions here. Here are some ones that you could find f prime of x for. I think the last 2 are pretty rough, though. The first 4 are reasonable. I'll show you the answer so you can check. So there are at least alleged solutions. There are also some practice questions in the book. I'm going to ask you to find the derivative function and then find the slope at the indicated point, because really the key here is us being able to find f prime of x. This is on page 105, do 137, then 9 to 12. And there are the solutions for those from the Finney 4th edition AP Calculus textbook. I hope that you found this useful. Now we can find this derivative function, so that's pretty neat, the slope anywhere. We have better notation. We don't have to say m tan anymore. Good luck with the material, folks, and take care.